Slideshow. So welcome everybody to our training for the day, which is on advanced cluster usage. I am Paul Edman. I'm a member of the data science research facilitation team at Fast Research Computing. I help run the scheduler and help maintain the cluster. You probably have interacted with me via tickets if you've submitted anything related to Slurm. I'm probably the one that answered you back on that. Today we're gonna talk through some advanced cluster usage ones. This presentation assumes you've gone to the previous presentations regarding basic cluster usage. We're going to be talking a bit more, some more advanced topics within the realm of using the cluster. We're not going to be able to be exhaustive about everything, because to be exhaustive would be its own class unto itself. It would just take way too much time that we have here. Instead, we're just going to take a kind of an overview of everything. If you have questions as we go along, please drop them into the chat. I will try to pick them up as we go along, or at least I will get to them at the end as we go. My screen is a little bit cluttered, so it's a little bit hard to see the way that Zoom has different windows all over the place. But I'll do my best to answer any questions you may have. So kind of as an overview of where we're going, we're going to talk a little bit about job submission to begin with, and then we're going to talk a bit about job resource requirements. After that, we're going to talk about job partition queue monitoring, how you monitor your jobs to do this most effectively. Then we'll talk about job checkpointing as to how you can make it so your code can survive being preempted or dying. And then we'll talk a bit about fair share, and then we'll close out talking about storage workflow and how we expect users to use our storage and use the cluster. So first, we're going to start with the very, very basics, just to kind of work our way back up into doing something a bit more advanced. So interactive sessions are the first and primary way that you're going to end up interacting with the cluster. And this is if you are just doing things via CLI, the command line interface, and you're just doing it text-based, and you need to get on a compute node because the login node doesn't have enough space for you. Because remember, login nodes only allow you to have one core and only allow you to have 4 gigs of memory to start out with. You can't get any more of that on the login node. Login nodes really aren't intended for heavy work. You really want to get onto a compute node. And so SLIC will give you that ability to get on a compute node in an interactive session. And so it's really useful for testing code or to work interactively on the cluster without resource contentions. You really don't, because again, if you're on a login node, you have limits, but then you're also competing against everybody else on that login node. There could be 50 plus people on that login node. And you really want to make sure you have your own allocation. There are some limitations with the interactive session when you're using it, namely that sessions that last for a while, if you don't use the prompt very often, the session can stall out, which means that things can just kind of hang there. You won't be able to use that session anymore. Similarly, it also ties up a prompt for you, and so you have to open up a new prompt in order to do something else on the cluster. It's really not great for GUI applications. X11 forwarding, which is what is used for GUI applications, tends to be rather non-performant via SLIC, via the interactive session. And if they're submitting to a busy partition, SLIC may just take a while to run. It may just take some time for it to actually get through and actually run on the cluster. That said, if you're just trying to get something quick and dirty done via the command line, SLIC is a fine way of doing that. If you submit it to the test partition, which is this -p test, you will pretty much almost always go immediately because test is set up such that there's enough idle capacity your job can run immediately, assuming you're not asking for more than one node's worth of stuff and not asking for more than half a day's worth of time. So you want to be careful when you're asked interactive sessions, scope those correctly and use them appropriately. But it is a really great way of kind of interacting with the cluster, especially if you need to do some testing on some actual nodes, and especially if you need to build something on a node. It's a really great way of kind of doing your work. If you need to do something that's more hardcore in terms of interactive, we definitely recommend using Open On Demand. Open On Demand is definitely the method that we prefer for doing interactive sessions. If you need to do something for like days at a time, or if you need a GUI, or you need to have multiple windows open, or you need to walk away for a while, it's a much more durable session than the ones that are via SLIC. SLIC can take a little bit of time to get through and will only give you for a certain amount of time. And if you walk away, it's going to get locked up. If you use the open on demand, though, you can ask for pretty much almost anything within reason. Asking for multiple nodes isn't really going to fly in terms of like with a single remote desktop. But if you need like a node for like several days, this can get you it. It may take some time to get you a node for several days. After all, you won't be able to submit to the test partition, but you'll still be able to get a session on the cluster that you can walk away from and be able to come back and be able to use again once it comes back. Plus, then you'll also be able to support all your normal GUI operations. You'll end up, when you click on the remote desktop option, you'll see all these different options. The partition is going to be important. Remember that the partition is the same as any other partitions on the cluster. So if you're spinning to the test partition, you're going to be limited to one node's worth of compute and then up to 12 hours. But if you use the test partition, you'll be able to go immediately. If you want to run for longer, you can always submit to the shared or Sapphire, or even if you really want to run for a long time, you can submit to unrestricted, and you can have a much longer run in that case. Just note that if you submit to those partitions, your job may pen for much longer as it waits for sessions to get going. Once the session gets going, though, your session is going to be open for a long time. I know some users, what they'll do is actually they'll submit chained open on-demand sessions. So they'll have one running and they'll have another one pending in the queue, so that when their current remote desktop session ends, the new one kicks on online. They're able to hop over that one without much interruption in time. So if you want to be super sophisticated, you can do that sort of thing if you really need a remote desktop open for that long. Generally, I don't recommend doing that, just because if you leave it open for too long, you may not have remembered to save your work, or you may have something important there that you can't lose. And we don't guarantee uptime in terms of the fact that if things go on for multiple days, it's entirely possible the node you're on may die or suffer some other fault that may cause your job to die. So actually getting the habit of opening and closing these sessions is actually really good, because it forces you to save your data and make sure that you're not just holding on to stuff that you should be able to close that's not important. Okay? So while interactive sessions can last for a long time, you don't want to just sit in it and park in it forever. You want to make sure that you can close it out, that you can get everything saved there. The interactive session open on demand all the fields there you see there, all the stuff you see there, all the different fields have different things you can do in terms of asking for GPUs, cores, amount of memory. You can even ask for different things in terms of time and constraints on your job in case you need to ask for a specific hardware. We'll talk a little bit more about that in a moment in terms of how you really kind of get your job submission and your job dialed into really what you want to do. When you get an interactive session, you get a nice little, if on open on demand, you get a nice little desktop here, which is really nice to be able to do. And you can open up multiple different terminals in here. And like I said, you can walk away from this and then it'll still be there if you get back in on on this interactive session. So it's really handy for being able to do a lot of different things, including GUI operations. The next thing we're going to be looking at is batch submission. Now, interactive sessions are fine and good, but those don't really scale. You can't really run like thousands of those at a time, although I know some users try to do that. It's not a very effective way of computing. It's not a very scalable way of working. So what you really want to get into the habit of doing is to really get into submitting batch jobs. That's really where the power of the scheduler lies, is really with batch jobs. Because really, if you're doing interactive sessions, you're not doing anything really you couldn't do on your local machine. The advantage of the supercomputer is not that our cores are individually faster than yours are. In fact, sometimes they're not. Instead, what the advantage of the supercomputer is that we have hundreds of thousands of cores, which means that you can run on tons and tons of compute without much of a problem, which is much more than your local machine can do. And also, you can also send it to the cluster and then walk away from it. And like, unlike with your local machine, where if you shut it off, everything stops, the cluster keeps on running and you don't have to worry about it when it keeps on going. So if you want to, so if you do batch submissions, you probably learned this in the intro class, you have a bunch of different options here. So you have the pound exclamation point bin bash, which tells us that this is a batch script. Then you have all the SBatch lines here, which are called pragmas, which are used to indicate that there's an instruction for Slurm in this line here, because normally pound and bash is a comment line, but pound S batch says, hey, this is an instruction for Slurm. Dash G, capital J is for the name of the job, which is really useful for job control. So if you have a bunch of jobs that are all named the same thing, you can use scancel to cancel all of them simultaneously without having to worry about like what the job IDs are. It's really a handy thing for to do. Dash N is for how many ranks you need if you're running an MPI job. Dash C is how many cores you need if you're running something that's threaded. And we'll talk about that in just a moment. Dash P is what partition you're submitting to. Dash T is how much time you're asking for in the format of days, dash hours, dash colon minutes, colon seconds. S batch, mem per CPU is how much memory you need per CPU you get, and it multiplies out. So each one of these, all 4 of these threads and all 32 of these ranks will get 8 gigs of memory. Then you have dash O, which is for the output file, and dash E for the error file. And this percent A says, hey, for this file, tag it with the job ID. Now, this is pretty important when you usually want to track what job IDs you're using. So tagging your jobs or your output files, or just dumping out somewhere what the job ID is really handy, because especially if you're troubleshooting, that's one of the first things you're going to need to know is what your job ID is, so you can back construct what happened. Especially if you submit a ticket to us, we need to know that job ID first and foremost, because otherwise we're not going to know how to troubleshoot anything. Then after that, after the SBatch lines, you have what you're actually running in the script. Right? The advantage of SBatch is that when you submit the job, it just kind of runs that to the scheduler, and the scheduler takes care of it, and you can walk away. You don't have to worry about it. It will run whenever it runs. Okay? There are several different types that we'll refer to in terms of different batch jobs. The first is serial jobs. Serial jobs are jobs that use one core and run their codes in a sequential manner, which is why they're called serial. Okay? Serial jobs make up actually the bulk of what we do on the cluster. Most of the jobs you'll see on the cluster are all serial jobs. People get parallelism, though, by submitting many serial jobs all at once. Okay? So this is what is known as embarrassingly parallelism, which is basically where you say, well, I don't have any way to parallelize my code, but I do have a bunch of different files I'm working over, or a huge parameter range I'm going over. And so I'm just going to submit like thousands of jobs, basically, and each one of those jobs will basically use a different parameter or a different file. And then I'll be able to run all those jobs simultaneously, assuming the scheduler gives me the resources. And I will be able to run those all simultaneously instead of having to run those like sequentially, which is really the power of that embarrassingly parallel method, is that it's pretty much, it will immediately give you parallelism for free without having to do much of anything other than organizing your code in such a way that it can, each run can pick up a different file or a different variable that it needs to use. An easy way to do embarrassingly parallel work is what's known as job arrays, which use the dash array instruction. Dash array can basically, in one job submission script, submit multiple jobs simultaneously from that one job submission script. Because normally for serial jobs, you have to submit them all individually. With the job array, you can have one script, you submit that script, and it spalates out into a bunch of different jobs, as many array elements as you have designed. And then there's a variable inside that script, inside that job, that you can then key your script into to then use to differentiate between each of the different parts of the array. Okay? So arrays are really useful, and we definitely recommend them for if you're doing embarrassingly parallel work, you want to run like thousands of jobs at once. It's a really light way to interact with the scheduler. The scheduler is much more friendly towards it. It's also easier to control from a job control point of view. The next way up in terms of parallelism, this is in terms of difficulty, in terms of as we go down this list, is thread-based parallelism. Thread-based parallelism is basically where you have a shared block of memory, and then you have a bunch of different threads that all can see that memory and operate on it. Okay? The things that do this, for instance, are OpenMP is a good example of a threaded application. Pthreads is another example of this sort of thing. Python multiprocessing is also a good example of a thread-based parallelism sort of method, where it uses fork to fork off different threads and streams as it goes. Okay? For thread-based parallelism, you need to use the -C instruction for asking for how many cores you need. Don't use -N, but use -C. And you're only constrained to a single node. So a thing that's in a threaded-based parallelism, you cannot expand over multiple nodes. The advantage of thread-based parallelism, though, is that it's usually pretty easy to implement. If you've ever seen OpenMP, which we have given talks in here about before, and if you have not been to a talk on OpenMP and you're interested in it, please come to one of our talks on that technology. It's really easy to put into C or Fortran code OpenMP pragmas that then will parallelize out do or for loops very easily. Similarly, if you're using like Python, there are easy ways to parallelize out using multiprocessing or various threading packages around that you have. R has its own recommendations in terms of threading. I don't remember them offhand. We do have documentation on our website, though, for R code on that. But a good question on R code. I don't remember what because R does actually have threading applications. Like I said, our documentation definitely has recommendations for R in terms of parallelization. If you can't find it in our documentation, drop a ticket to us. We can definitely direct you, point you in the right direction for that. I just don't remember R offhand as to what it's called, because R has its own packages that do its own things internal to it, and they're all strange. I don't have them all memorized, so I can't give more guidance to that. But it's really powerful and actually is the easiest way to parallelize aside from doing like array jobs or brute force serial jobs. It does take a bit more finesse to do because it does take you to modify your code or use a package that has the ability to use it. The next level up is called rank-based parallelism. Rank-based parallelism is what's used by MPI, which is what's called message passing interface. This allows you to use multiple nodes because basically what rank-based parallelism says is that each process has its own rank, and that rank has its own memory allocation, and every rank cannot see the other rank's memory allocation. So ranks have to pass messages back and forth between each other so they can communicate back and forth. Hence, message passing interface, MPI. What this allows you to do is that you're actually able to use multiple nodes in this method. So I could have a node on one side of the cluster, a node on the other side of the cluster, and I'd be able to pass messages between those nodes and be able to do things in parallel. So all the most powerful parallel codes are all written in MPI or in this method of being able to do rank-based parallelism where they're able to pass messages between nodes. Doing that is tricky. It is not trivial to add into your code. You usually have to consciously implement that sort of thing. R has RMPI, which you can use for that. RMPI is easy to remember. It's one that I actually do remember. Python has MPI for Pi that you can use for this. But if you really want to get the most power out of your application, you really want to go to C or Fortran and use MPI natively and do it that way and orchestrate your own code. It's very tricky. It is not easy to do. If you're going to write an MPI code, definitely budget like a couple months to do it because getting all the nuances right is difficult. And if you get things out of order, you can create deadlocks and things can be a little bit tricky. But that said, if you get it working, it's going to be very powerful in terms of being able to really utilize the cluster. And this allows you to go beyond like hundreds of cores to now thousands of cores in a single job and be able to run some of the largest types of code in the world is using tools like MPI. Finally, you have the hybrid approach, which is used by the very largest codes in the world. And this hybrid approach basically says, okay, well, let's take the best features of rank-based parallelism and thread-based parallelism. So actually, this submission script I have here is actually an example of thread-based parallelism and rank-based parallelism. What this does is that you say, okay, well, I'm going to have a certain number of ranks, and then each rank is going to have a certain number of threads. And so in this case, we have 32 ranks, but each rank has 4 threads, meaning that this job submission script is actually going to use 128 cores. The advantage of using this method is that you can really cut down on communications overhead. So if you're running on some of the largest machines in the world, you may have thousands upon thousands of nodes, and those nodes need to communicate with each other. But if you have thousands of ranks per node, that can create a huge logjam in terms of communications. Whereas if instead you create a bunch of threads, and those threads report back to the rank, and the rank then is the thing that communicates back, you've now cut down your communications dramatically that way. And you can create better efficiencies when you get up to the very largest scales. Now, typically on the scale of Canon, you're probably not going to really need hybrid situation. But if you are using a larger machine than Canon, so if you're using a Canon as a test bed for, say, going to a national lab using one of those machines, or going to some other resource that you have access to, doing those small-scale tests on Canon are really useful because then you can go to that larger machine and have confidence that it will actually run, and your code is ready to go. Okay? So those are different types of parallelism. I'm going to go through some really useful options that exist within Slurm that can really help tune your job in terms of kind of showing what you really want to do in terms of kind of dialing in the job efficiency. As a note, the more constraints and more things you add to Slurm in terms of telling it what to do, the longer your job's typically going to take, just as a general rule. So you generally want to run with the least number of constraints you possibly can. Okay, you want to avoid that as much as you can in terms of adding constraints. But sometimes your code really does need those constraints, really does need those extra things that will kind of shape your code in the way that scheduler handles it, because it'll improve the efficiency of your code. If that's the case, then definitely include them. But as I noted, you want to include the least amount of that, so that way you can get to the scheduler faster. Okay? Because your time to science, your time to actually a solution is a combination of how long you're pending in the queue for and how long your code is running for. And the sum of that is how long it takes for you to get to a solution. And you want to minimize both of those. So if you can give up time in terms of scheduling time and gain a little bit time in terms of runtime, if that total ends up being less than you would normally get to, you want to go that route. Even though your job may run longer, it's going to spend less time in the queue, which means you got to the solution faster even though for that one run, your job actually didn't run very fast. It's kind of a little bit counterintuitive in terms of how it works, but it actually is, once you get your mind into it, it's really useful. So useful options, and the Slurm documentation is full of these. So I invite you to read the sbatch and srun documentation, which basically has a bunch of these different ones. I'm just going to briefly describe each one of these. So -- contiguous as an option means that you will get a contiguous block of nodes in the scheduler. Okay, the way that we have nodes named on the cluster is named by where they are on the cluster in terms of proximity to each other. And some codes really care about topology and where their different parts end up, so that way you can have best communication. If you want to make sure that all the nodes you get assigned are adjacent to each other on the InfiniBand fabric and are all adjacent to each other from a network point of view, right, you want to include -- contiguous, because that means the scheduler will give you a block of contiguous stuff. Okay. If you don't specify that, Slurm will give you whatever resources it can find wherever it can find it. Okay. And that could be just kind of like, you could have like one core over here, 100 cores over here, and another core, like another 20 cores in the middle, and all over the place. And it may not be a very good layout for your code if your code is not set up to handle that sort of random layout. I haven't personally used Future, Yishen, on the cluster. I know some of our other staff have, so I would drop in a ticket to us and we might be able to give you some guidance on that. I know some of our staff have looked into using Future. So I definitely would drop a ticket to us. If we can't answer it, we'll at least try to direct you to some resources that will be able to answer that. Okay. Other useful options that are out there: -- constraint. If you need to specify, hey, I need to run on an A100 node. I need nodes that have A100s. -- constraint will say, okay, this is the way that you specified that. Or let's say I need all Sapphire Rapids nodes. -- constraint can set that for you. You can even, the lesser constraining version of constraint is -- prefer. So you say, I don't really care what node I want to run on, but I would really, if I could get an H100, I really would prefer that if at all possible. If you do -- prefer, that will say, okay, I'll try to find H100 for you if I can. If I can't, they'll give you whatever I can find. So that way it will prefer to go to those other resources, which is really handy if you really want to try to get the most out of your code and you really want it to run fast, but you don't want to kind of constrain yourself too much. -- dependency is really useful for if you have one job that depends on another job. So say you submit a job and you need to wait for that job to run before the next job runs, but you don't want to wait and watch for that job to finish. You just want the scheduler to handle that. -- dependency can do that for you by just saying, hey, look for this job to complete and then you can run. -- dependency will do that. Dependency has a bunch of different options as to different states it can get into, how you can specify what will complete. So read the documentation for more information about that. -- exclusive is something that we don't recommend, but is useful if you need to make sure that no other users on a node than you, or if you use the equals MCS option, no other user outside of your group. This is very handy for things like FASI. If you have some sort of secure computation that you need to do, and you don't want the possibility of anybody seeing what you're doing, Dash Dash exclusive was what allows you to lock down that node to just you and nobody else, or just you and your group and nobody else. Use it judiciously, because Dash Dash exclusive can create all sorts of havoc within the scheduler in terms of your job may pen for a long time because you're using it. But it is a useful tool if you need to make sure yes, I'm the only one on this node. Dash dash GPU or dash dash gress is how you allocate GPUs on the cluster. And you can also specify exact type. So dash dash constraint only gives you general class. So if you need any A100 on cluster or any H100 on cluster, dash dash constraint is what will get that to you. But if you need, say, oh, I need an A100 with 80 gigs as opposed to A100 with 40 gigs, dash dash GPU or dash dash gress is what you're going to want to use to allocate that specific type of GPU. That's the way you do that if you need to do that sort of thing. Dash dash temp is how you allocate /scratch space or local scratch on the node. So if you need to say, hey, I need local scratch for, say, I have like a large language model that I'm going to be doing and it needs to talk to disk a lot, and I need like 100 gigs of disk on the local machine so I can just talk to it all the time. That's what dash dash temp is for, is to say, okay, make sure that I have this much space on this node when I need to use temp space, so it's all there. So that's a really handy tool for that sort of thing. So now we've discussed job submission, let's talk about looking at how do you decide what your requirements for your job is. Now, we have a very exhaustive document on our website for job efficiency and job optimization. I invite you to go read that because it has a lot of great information in it. I'm going to be going through kind of the high level overview of that document, essentially, in terms of what's contained therein. The most important things that you need to know about when you're doing job optimization and doing job resource requirements is knowing your code. Okay. Generally, you should try it the best you possibly can to make sure your code is not a black box for you. Understand the algorithms, you understand what your code is doing on the back end of it. And this goes for code you haven't written. This goes for code you have written. You should always understand what your code is doing, because otherwise you may run into some situation where the code is not producing useful results, or you don't understand what mistakes your code is making. Okay? Knowing your code also allows you to kind of dead reckon how much memory you actually need, right? Because you know the numerical methods that your code is using. If you don't know that because you just don't have time to figure it out, or your code is a black box and you have like no way of getting through the impenetrable layer of what the heck is going on in that, you can then try some guesses as to what the amount of memory you're going to need is. Okay. Typically, a first order guess as to how much memory you need is going to be the size of data that you're going to be ingesting. So if you have a file that's like, say, 100 gigs in size, you're probably going to need 100 gigs of memory to hold that in memory. Often, though, the numerical method you're using may in fact require multiple replicas of that in memory. So you may in fact need 2 or 3 times the amount of size of the data you're reading in memory to be able to operate on it. Yeah, it depends on method. The other way is that if you know the type of parallelism you're using, you can also come up with good estimates as to how much space you need. In terms of like, okay, well, I know that my code is a thread-based parallels code. I know that it expands, like every time I increase the number of threads, it increases the amount of memory by the same factor as the amount of threads I increase. Right? So I know that if I double the number of threads, I'm going to double the amount of memory. That may be the case for your code. Alternatively, like you're using a rank-based parallelism code, and you're like, okay, well, I know that each rank is going to need at least 8 gigs. So I'll use 8 gigs per core as a metric. And that way I don't even need to change anything. It just naturally scales with the amount of cores I have. If you don't know your code very well, or if you don't have a good guess, experimentation is always a way to get around. You can do this. Experimentation basically is what you do is basically you ask for way more than you actually need. And then you look after the fact at how much you actually used. In this case, the tool that we recommend for doing that is SEFF. So if you use SEFF, and then the job ID will give you this nice printout about the job in terms of its efficiency. Okay? So in this case, you can see this particular job. Okay? It ran over 8 nodes, it has 64 cores per node. It used up all this time, but in terms of efficiency, it was only 23%. It was only 24% efficient. meaning that we really need to look and probably should reduce the amount of cores we use by a factor of 4. Okay? So we probably should reduce the number of nodes we use maybe by like to 2 nodes instead of 8 nodes. Okay? Because this code did not scale and use up all the cores we gave it, and we wasted a ton of time here. Okay? Likewise, you can see how much memory this thing used, and you see that this node, this job used up all the memory it was allocated, which is really good. That's what you want. Okay? But if you end up with, like, say in this case, let's say it was using like, 0.5 terabytes, something like that. Well, that means that we're at 1/3 efficiency for memory, meaning that we should cut our memory request by 1/3. What I do recommend, though, is that you never want to this run here was fairly risky. You never want to get to the point where we're at 100% memory efficiency, because if there's a little bit of noise on the memory allocation in terms of how much it's allocating, you may hit the limit of the job, and your job may exit due to out of memory error. Okay? So you always want to keep a buffer of about maybe 5 to 10% on the top. That's usually what I do. So a memory efficiency of about 90% is pretty good. You don't really need to get more efficient than that if you're doing that. Yeah. So always look back, and you can go back and analyze your job and say, okay, how much did I actually use? Okay. And if you want to do it for a bunch of jobs, let's say like you have just like, okay, what did it over the last month? I'm just running the same job over the past month. How have I been doing over the past month? You can use the tool SEFF-account, and it will allow you to show a graph of what your usage is. Okay. You can also do scaling tests on your job. So you can say, okay, if I have a parallel job and I double the number of cores, does the amount of time my job take half? Because if you have a perfect scaling, your job should, every time you double the number of cores, the amount of time it takes should scale commensurately, and so get halved each time. Okay. If you do a scaling test, though, you may see a point where your job has a point of diminishing return, where you will no longer see that increase by a factor of 2. It may be like a factor of like 1.5, or like 10% or something like that. In which case, it's not worth throwing more cores at it anymore, because you've hit the limit of what your code can do in terms of performance. And in that case, you probably need to start thinking about re-architecting code to figure out what you need to do. You can also profile your code. There are several profilers that exist that you can use. vTune is one that we have with the Intel cluster suite, which you can use to kind of profile your code and kind of get a feel for how your code is performing. If you're doing GPU stuff, NVIDIA has a bunch of different GPU tools you can use for profiling. Weights and biases is also a method you can use for code profiling in terms of seeing performance, especially if you're doing stuff via Python. There's also things you can do that if you don't have a tool as convenient, you can use SStat or SAtCount for kind of doing your profiling. So SStat is the tool you use for getting information on your job as it's running. SAcount is for when the job is done in terms of the information. So if you ever look at SAcount while a job's running, you'll notice that a bunch of it is empty. It'll say the state, but it won't say like how much memory you're using or anything like that. SStat is the tool that has that information. So if you wanted to, a very cheap and easy way of profiling, you could just set up a loop that just said like every 5 minutes, just dump out what SStat says and show me and give me the results and dump it to a file. And then you can look at that after the fact, say, okay, how did this look over time? How does this evolve over my run? And get some information of what's going there. SStat can be really useful for that. And then finally, you want to select the appropriate partition and hardware. Okay? You want to make sure that your code is architected for the hardware and partition you're using. So for instance, if you built your code against Sapphire Rapids, you're not going to be able to run against anything that's not Sapphire Rapids. However, if you built it more generically, you could run it against anything on the cluster. Right? Likewise, if you built a like PyTorch or something like that for the A100s, it may not run on the H100s. You may have to rebuild it for the H100 and be able to do that. Whereas you built it more generically, you might be able to run on both. That said, if you build it for a specific host, you may actually get massive performance increases because you built it for that specific thing rather than a generic sort of thing. So you generally want to kind of choose what's going to be most effective for what you're trying to do and what's going to scale your code best. Likewise, if you are able to, it's usually best to use the Riku partitions, both because they have a ton of hardware in them, and also because we charge half as much for fair share there than we do anywhere else. I just mentioned SEFF account. So this is a way that you can basically get statistics and get a overall statistics on your job similar to SCFF, except in a more expansive way with these nice graphs and everything like that. And you can set a time, start time and end time, so you can see everything like that. If you don't include a start and end time, it just shows it for the last day, okay? And gives you a summary for your user for this. -A you can use for your account. You can't show it for jobs outside of your user. We can elevate privileges for certain people in your lab, so you can get overall lab reports on everything you want to do. Or you can ask us to pull a report for your entire lab, so we can give you information as to how your lab's performing and what's going on here. So, for instance, this particular user, their CPU unit efficiency, most of their jobs are not very efficient. They're not doing much of anything. There's this nice peak in here that's about 50% efficient, probably two different classes of jobs going on here. And so they really should look at this class of jobs here in this nice Gaussian here at the 50% mark, and probably need to either half the number of cores they're asking for, or make sure that this code is actually parallelizing properly. And then one that's down here at 10%, they really got to take a look at these jobs and see what the heck's going on with them. Likewise, with memory efficiency, you can see the vast majority of their jobs don't use up any memory at all, whereas only a very few jobs use up the memory they do. So it'd be really beneficial for them to be able to classify all the jobs that don't actually need a bunch of memory and request less memory for those. And for all the ones that do need more memory, they should really make sure that they are actually for the memory you need. Likewise, for time efficiency, you can see here, these jobs are not using nearly as much time as they need to use. So these users can increase the amount of time that they're requesting by a good fraction. Okay. So it's a really useful tool to be able to see all this. You'll get averages over here, so you can get kind of an estimate here. So like, for instance, like this group is using like, actually for an average of 8 cores and is really only using like 15%, which means they're really only using 1 core. So they really probably should only be asking for 1 core. Their code's not actually really parallelizing. Similarly here, like they're asking for 120 gigs, they're only really using 4. So they really should only be asking for 4 gigs here. And in this case, they're asking for 2,000, they're only really running for 2,000 seconds. So they really should only be asking for about maybe like 3,000 seconds or something like that to cover most of their jobs. So it's kind of, this just kind of a really quick estimate for kind of what's going on with your work. Here's some graphs about scaling, so you can see what I was talking about before. So strong scaling, basically what you're doing is you're keeping the computation constant. So it's the same computation, but you're just increasing the amount of cores you have thrown at it. Okay? You notice this is a log plot. Okay? You'll see that you got this factor of 2 each time, okay? Until you get up to about 250 cores or so. And then at that point, you see it starts diverging from that line. So this is the ideal increase, but you see this is diminishing returns at this point. So really, I shouldn't really ask for more than 250 cores here, because if I try to ask for any more, I'm really just getting diminishing returns. I'm not really seeing much any benefit for that. Okay? Similarly, you can do what's called weak scaling. Weak scaling is where you grow the computation in proportion to the amount of cores you have. This is a test of the communications fabric and your communications overhead. And you see here, in weak scaling, as your computation grows, and if it grows in proportion to the number of cores you ask for, the amount of time it takes for your job to run should remain flat. It shouldn't change at all. Okay? We can see here, when you get up to about like 200 to 500 cores, this is a log linear plot here. You can see it's starting to diverge pretty dramatically. So you probably don't want to get above this point. It also means that you probably have some sort of communications thing you need to analyze here to scale up to even further than this. These tools are really useful for parallel applications because it'll help you gauge how many cores you really should ask for, and also help you find weak points in your parallelization method and be able to get pushed past those. You can get even more scaling as you ask for even more cores. SACT, which I've talked about before, is a great way of monitoring your jobs. We recommend this over using SQ. SQ is a buffered way of looking at your current usage, and it isn't live. SACT is almost live data, just like SQ is, and can give you that information with less impact on the scheduler. Okay? You get a bunch of different information there. Everything you would get via SQ, you can get via SCount. So we definitely recommend that. Get a bunch of different options in terms of start time, in terms of formatting it. You have the parsable format, which make it easy to feed it into scripts if you needed to. You can ask for a different which partition, gate it by partition. You can ask for a different state. So SCount is really a good way of kind of looking at your current usage. You want to look at the usage of the queue and as a whole, using SQ or using show queue is kind of the way you want to go about that. If you want to get information on your job in terms of really detailed information, it's like what the heck is going on with this job, scontrol show job and the job ID will give you all that information. So this is basically the most that the scheduler knows about what your job is doing. And this includes things like what your state of your job is, whether or not your job has been preempted, okay? What the runtime of your job is currently. If your job is pending, it will list you with a projected start time if it has one. So if it, and also under reason, if your job is pending, it will list the reason if it has one. So if it says reason resources, it means your job's waiting for resources to come free. Okay? If your job is sitting there in priority, it means that there are other users ahead of you in the queue before you run. Right? And then the start time will give you a good reference as to when your job is going to start. End time tells you when your job's going to end in terms of when it's going to time out. Right? Node list will show you what node you're on, which is really useful if you want SSH to that node and take a look at what's happening. Okay. And then you have all the different allocation parameters and what you're actually using in terms of resources, all listed out here, which is really useful for being able to see what you actually got assigned to and what you're actually using. Show queue, which I mentioned a moment ago, is a good way of getting an overall view of the state of the partition. Okay. It'll show you basically how many cores are available, who's next in the queue, who's in the queue, who else is there, so you can get a sense of what's going on. If you use -P, it will do it by partition. -O will order priority. So if you don't include -O, the order of the waiting jobs is somewhat random. But if you include -O, it will order the pending jobs by priority. So that the top job is the next one to run. So you know, like, okay, I know my position in the queue now, and I can see where I am. I can kind of estimate when I'm going to go. Okay. -U will specify only your username, so it'll only show your job specifically. And if you use -S, it'll give you just a summary, just this middle line here on how many jobs are running, how many cores are running, what's used, and what's available. Okay. So show queue is usually the way I look at the queues to see how things are flowing, to see how people are running. You can get an estimate as to how fast things are flowing through the queues by looking at show queue. If you regularly just kind of look at it, you can just like kind of get a feel for how the queues are operating and when things are vacant. So it's definitely a very powerful tool for being able to get a feel for what scheduler is actually doing and get a view as to cluster state. So a tool that we definitely highly recommend to all users is job checkpointing. The reason why you want to do this is because jobs will not always run to completion correctly, either because they run to a fault on the hardware or because something else that happens, your job will die. Okay? And you need to be able to do that. Or alternatively, you need to run a job longer than the queue length is for. So you have a job, you want to run it for several months. Okay? The maximum queue time is only 3 days. Well, you can use job checkpointing as to bridge yourself to those several months by basically restarting the job every time. Okay? Job checkpointing, what it does is basically just create a save point for your job that you can pick up from. Okay? Basically, your job writes to disk everything it needs to know in order to pick up from where it was. Okay? There is no way of doing this from Slurm natively. Slurm does not support job checkpointing in terms of like doing it automatically for you. You have to code or develop your job to be able to do this. Okay? So you have to build it into your code, which is usually the best way of doing this because you can really dial into what specific things you need and be able to come up with a good method of doing that. If you don't have control over your code, a way you can do this is use DMTCP or distributed multi-threaded checkpointing. What this does is basically it just does the very brute force method of just taking a memory dump of everything in memory and dumping it to disk. As you can imagine, this can take up a lot of memory if you have something that's using up like say like a terabyte worth of memory or something like that. If you use DMTCP, your thing's going to use up a terabyte memory on disk. It also, your code may not recover properly when using DMTCP, so you're going to want to test that if you're going to try to do that. However, if you can do this, you can then use things like dependency, and then you say, okay, well, I have a job and I want to run out for a month, but the maximum runtime of it, but I don't want to wait in unrestricted for like weeks on end to get to unrestricted. And also the cores on unrestricted are slow. I want to run on something that's faster. Well, let's then say, okay, well, I've got to submit this job, and then I have a job that has a dependency, And when that job exits, the dependency will execute, run the next job. The next job will say, oh, I'm running the same job and I see I have a restart file here. I'm going to pick up from where I left off and keep on running. And that way you can bridge yourself into jobs that run out for months at a time if you need to. Likewise, if you want to use like serial requeue or GPU requeue, okay, you can make your job aware of that and say, okay, well, my job got preempted and I can see that I have a restart file here. So I'm just going to pick up from where I left off because I see that restart file and I'm going to keep on running and I don't lose that time that I had within requeue. Because when preemption happens in requeue, that time that you lost, okay, the scheduler doesn't refund that to you in terms of fair share. Okay. Your job will start, and the scheduler will start it as if it thinks it's starting from scratch. It doesn't know any better. It'll give you the full time you asked for again. Okay? But the time that you wasted there is something that scheduler still charges you in terms of fair share. So it behooves you to be able to restart your applications and be able to use the requeue in an effective way where your job will restart and pick up from where left off once it's preempted. Okay? And you can develop your code to be able to do that if you have checkpointing built in. If you need even to use DMTCP to do this, well, you have to be a bit more sophisticated in pulling tooling around it to get it to go. Right. I've mentioned fair share. Let's talk a little bit about fair share and what it is. We're not going to go into incredible detail here. We have a fair share document which goes through this exhaustively. So I definitely recommend reading that because it'll give you a really good view here. I'm just going to give you an overview of what fair share is. So fair share is a portmanteau which does exactly what it says on the tin. It basically makes sure that you as a user and as a group get the resources that you have been allocated on the cluster. You get a fair shot at the cluster and the resources that are there. Right? Basically, fair share tries to make it such that actual usage's lower graph looks like the upper usage on allocation. Okay? Now you can see that those don't look the same, but fair share is trying to get it such that those two graphs look the same as each other as much as it possibly can. Okay? Basically, fair share allocates to you a certain slice of the cluster and says, you have this much of the cluster to use, and that's what I'm going to try to give you that too. The score, fair share score, is assigned to a user and group based off of usage. Okay? And the amount of allocation you're granted is based off of two factors. One is the gratis fair share that everybody's given. So by virtue of being part of the cluster and by virtue of the investment that FAS has made in terms of buying hardware, okay, there's a certain amount of fair share that you just automatically have as being part of the cluster. In the case, if you're on Canon, it's a fair share of 200. And if you're on, it's a score of 200. If you're on FASI, it's 100. And but effectively, what that means is that means you have access to effectively 200 Cascade Lake cores. Okay. So you can use 200 Cascade Lake cores, which is the cores on shared ad infinitum. So if you were to run a job that used 200 cores and it ran off to infinity, okay, you would exactly use up your fair share. Okay. So that's what the score kind of does and means. You can also have a higher score than 200 than the base score because users can also buy additional hardware that then we add in as additional fair share that you can have. And that increases your score, and that therefore increases your fair share. Okay? So the fair share score then is calculated, and so we have the difference between raw shares, which is the number I was talking about just now, your allocation, versus fair share score, which varies between 0 and 1. So a fair share of 1 means that you haven't used the cluster at all lately. Fair share of 0.5 means you use the cluster exactly as much as you've been allocated. And a fair share of 0 means you've massively overused the cluster. Okay? And if you're above 0.5, it means you've underused your allocation. If you're above 0.5, if you're under 0.5, you've overused your allocation. And your fair share score goes up and down depending on your usage and the usage of your users. Okay? And then the priority you get in the queue is based on your score, priority score, fair share score versus other users. Okay, so priority is made up of two factors: your fair share score plus how long your job's been sitting in the queue. Okay? So the longer your job sits in the queue, the higher your priority gets in the queue, even if your fair share is 0. Okay? You'll naturally gain priority just by sitting in the queue. So what matters with priority, though, is your score relative to other users. So for instance, if you have a fair share of 0.9 and you're sitting in a queue, but somebody else has a fair share of 1, they're going to run ahead of you in the queue because they have a higher priority. Okay? However, if you're 0.9 and everybody else in the queue is like at 0 or something like that, you're always going to be first. Likewise, if you're like sitting at fair share of 0.1, yeah, you're probably going to be a bottom feeder for a while, but if somebody is below you at 0, you're going to run ahead of them at all times. And if nobody's above you, you just keep on running. So even users that have below 0.5 of fair share will be able to run because the scheduler tries to fill in gaps and always tries to have everything populated as much as it can. So if you are sitting in the queue and you're at fair share 0 or close to it and nobody else is in the queue, the scheduler will give you resources even though you're fully exhausted your fair share, because it wants to make sure that all the resources are utilized. It would rather have all the resources utilized than you sitting there pending. So even those who have low fair share are not without hope. You can definitely get resources still, even with low fair share. If you want to see what your S-share is, you want to see a breakdown of it, you can use the tool called S-share, which will give you a breakdown of what your current usage is and your score. So what I was talking about before, the raw shares here is this number here, this 244. Okay, and you see the default raw shares as I was talking about. And then you have your raw usage, and then the effective usage on the cluster, and then your fair share score. And here's the ranges I was talking about just a little bit ago in terms of different regimes you end up in. So like in this case, with this test lab here, you can see that this group has underutilized their fair share, and thus probably is going to get through the scheduler pretty quick because they'll be much higher priority than their users are in terms of running. Right? If you want to know kind of what fraction of the cluster you've been granted, this norm shares is basically the way you get that. So this norm shares is basically the percentage of the cluster you've been granted. Right? So in this case, this user has been granted 0.1% of the cluster. Okay. And the users have used 0.5%, 0.05% of the cluster. Okay. So they're basically halfway through their allocation, essentially, in this. Okay. That kind of gives you a feel for how much of the cluster you're using. The cluster is a big place. We have hundreds of thousands of cores, and we have hundreds of groups using it. So your fraction of the cluster is a smaller fraction of that cluster. But you can sometimes get much higher usage. I've seen labs who have a fair share of like 200 over here. So they only get like 0.1% of the cluster, who have used up 10% of the cluster. Now the fair share is 0 and will be 0 for a long time, but they managed to successfully use up a huge portion of the cluster and be able to get a lot of compute done for that reason. Yeah, just because your fair share is 0 doesn't mean you're out of luck. You can still get allocation and you still get throughput. You just may have to get a little creative. If you need to do some estimates of how much your jobs are going to use, if you want to say, okay, well, I don't want to exhaust my fair share. I really want to dial in how much my fair share is using. There's a tool called scalc that you can use that will calculate various different things in fair share. Such as, okay, well, if I want to buy more shares, how many shares should I buy? Or how much raw share do I need to buy? Or like say, like my fair share score is terrible, and I want to see how much time it's going to take me to get back to a reasonable fair share score if I don't run any jobs. Those first three will do that. Likewise, option 5 will basically say, okay, well, if I buy hardware, what am I going to get for that? If you choose option 4, though, it'll basically say, okay, well, give me an example job, and then let me tell you how much your job's going to cost in terms of fair share, so I can see what the impact on my fair share is. Okay, so you see here this particular user, okay, asking for 1,000 cores and 4,000 gigs of memory because he's asking for 4 gigs per core, so it's going to be 4,000 gigs of memory. So I asked that for a day. It's only running one of these type of jobs. It says, okay, well, if you run that job, your fair share currently is 0.97, which is pretty dang good. But if you were to run that job, it's going to cost you this much stress, and then that's going to create a new normalized usage of this much, which means that you're going to go from a fair share of 0.97 to a fair share of 0.63. So you see how much this thing impacted just for that one job of this scale. So scalc is really useful for getting a feel for how much your job is going to allocate, so that way you know ahead of time what your job is going to do to your fair share. And that way you can budget properly and make sure, okay, well, if I submit this regularly, I know I'm going to blow through this much, so I should only do so on this cadence, or I need to wait till my fair share is back to this much before I exhaust it again. So it's really useful for, especially if you're planning as a lab, to make sure you don't blow through your entire allocation all at once. Okay, so our final topic here, and we're just about at time, is storage workflow. So it's really important to understand how your job interacts with the storage on the cluster, because that will impact how your code behaves and interacts with different things. It's also going to impact how much storage you need and what you need in terms of storage, okay? And where you store different things. So the workflow that we expect for you to have, this is kind of the archetypical workflow that we kind of ideally would like you to do, is that you put your scripts and software in your home or lab directory. Right? If you need to share it with your lab, if you like have a lab collective, like just block of software, put it in your lab directory. So it's saying for you, put in your home directory. Okay. Home directory should store things you absolutely cannot lose, because it's snapshotted and backed up, but it only has 100 gigs. So you should only put things there. You're like, I cannot lose this. If I lose this, it's the end of the world. Like it's really bad if we lose this sort of thing. Right? Lab storage is your lab directory is kind of more for like, okay, when we put software here, but this stuff in your lab directory isn't backed up and it isn't snapshotted. So you shouldn't put things here that like you absolutely cannot lose. It should be things that like, oh yeah, I can recreate that, or something that's easy to rebuild. There's just common tools for the lab. Right? If you need to do raw data, you put your raw data in your lab storage. Okay? And you make sure that you buy whatever lab storage you need that equals the amount of tolerance you have for loss. Okay? So if you buy like tier 0 storage, you have no backups and you have no snapshotting, but you may need like petabytes worth of storage, and it's much cheaper to buy that storage. And you're like, it's not really be that high of a chance of me to lose data. By the way, we very rarely lose data. The chances of us losing data are very small, but it's not zero. We have lost data before, and I'm not going to say we're never going to lose data again. It will happen. Or alternatively, what was more likely to happen, you'll accidentally delete the data just by fat fingering something. Okay. That's the more likely thing to happen. And if you don't have any snapshots or backups, you're not going to be able to recover that data. So make sure you have storage that is commensurate with the amount of security you need for that data. Okay. And make sure you have backups. If we're not providing a backup for you, you should make sure you have a backup yourself. Right. You can always back up things like you should always have scripts and software in Git. And you should always have, if it needs primary storage, if we don't provide a backup, you should have a backup sitting on your desk somewhere that's in like a hard drive, something like that. Right. So you put your raw data on a lab storage, you put your scripts and software in your home or lab directory, and then you move what you're actually going to do to your Scratch. In this case, NetScratch. And I'll use this as an opportunity to say, if you're on Holy Scratch, get off of Holy Scratch, move to NetScratch. It's a better place to be. You then, when you actually run your jobs from the cluster, you interact with Scratch. And that way you're not touching lab storage or home directories. And the reason why you want to do this is that your Scratch directory is designed for high throughput IO. It's for being high performance. It's designed to take a punishment from the cluster. Your home, your lab directory, your lab storage is not architected that way. And so if you try to run jobs against it, you may cause the storage to crash or to grind to a halt and become very slow. So if you've ever been on storage, it's like, why is everything really slow? Well, somebody's running jobs against it. You shouldn't do that. You should avoid doing that as much as possible. If you want to avoid that slowness, use Scratch for your production stuff, and then move your analyzed data from Scratch to your lab storage. Okay. So that way you have the data, you can save it. Because remember, Scratch is temporary space. We have a 90-day retention policy on Scratch. So stuff that's on Scratch, been there for longer than 90 days, we remove. Okay. And there's no backups for that data, and we don't keep snapshots of it. So if you ever need stuff on it, so you should always make sure you have a backup of whatever you care about on Scratch. Right. For stuff that you no longer need, that's like data we published or data that like is inactive, I may need it like years down the line or months down the line, but I don't need it now. Consider putting it on long-term storage like tape or like cold disk, where you can pull it back and bring it back within a few days' time. But it's not something I need like right now. That way the one thing is that the storage is much cheaper than regular lab storage or lab directory is, which is really good for what you need to do. And also is designed for long-term storage. So you really want to make sure that that the data is on there. And you also will force you to curate the data, which is also really important. You should always make sure that you understand where your data is going, how it's organized, how it's laid out. Because if you don't start doing that initially, you're getting into a problem later on where like, where's my data and what's going on with this? And I lost it, or I have no idea, or some other grad student's going to come along and be like, how do I interpret this? This doesn't make any sense. And then you also explain it and you're like, oh, I really wish I'd organized this beforehand. Or alternatively, you leave the group and you didn't hand it off to anybody. And the next person comes up is like, I have no idea how to use this. And they'll basically burn a lot of time trying to figure out how to use the stuff you formerly used that you knew how to use, but they didn't know how to use. So documentation, proper layout of storage and directories is really important. Okay. So that's pretty much it for this. We have our training survey here, which I'm going to drop into chat. So we love your feedback. So if you can, please do fill that out and give us feedback for here. Also, I'm here to take questions for a little bit longer. I do have a meeting I have to take off to very shortly. But if you have any questions, please drop in the chat right now and I will go ahead and answer them. If not, thank you for your attention and have a good day.
Thanks, Paul.
No problem.
Thanks, Paul.
Hey, Paul, could you send me a link to this recording after?
Yeah, so it'll be posted on our website.
All right, thanks.
Yep. I'm not seeing any questions, so let me stop the recording, stop sharing. All right, good day.